Okay, so we're going to do an example, and we're going to apply separation variables in Cartesian coordinates. And here the example is going to be of an infinitely long rectangular metal pipe of sides A and B, and which is grounded. But at one end, which is at x is equal to 0, there is some potential. And the potential is V naught and depends on y and z. Now what we want to do is find the potential inside the pipe. Now, the first thing that we're going to notice is that this is a three-dimensional problem. So for Laplace's equation, this is going to be equal to 0. Okay, so that's the first thing. Laplace's equation in terms of x, y, and z. Now the second thing we're going to do is we're going to identify what our boundary conditions are. Okay, so the second thing is highlight the boundary conditions. Okay, which I'm going to call BC here. Okay, let's take y. What happens at y is equal to 0? Well, at y is equal to 0, the potential is going to be equal to 0. So V equals 0 when y is equal to 0. What happens when y is equal to a? Well, when y is equal to a, V is going to be equal to 0. What about for z? Well, for z, V is also going to be equal to 0 when z is equal to 0. For z is equal to b, V is also going to potentially be equal to 0. So V equals 0 when z is equal to b. And now let's do the x's. So I've left the x's off until the end because it's a bit more interesting. What happens whenever x goes to infinity? Well, whenever x goes to infinity, the potential is going to go to 0. Okay, so potential goes to 0 as x goes to infinity. And our last one is what happens at x is equal to 0. Well, at x is equal to 0, we're going to have a potential. So the last one is V naught. It's dependent on y and z, and that's for x is equal to 0. Okay, so that was our second step. We've identified our boundary conditions. Now the third step, and as always, what we want to do is we want to find solutions which are products of the functions, and they depend on only one coordinate. So we're looking for a solution of the form x, y, and z. So when we substitute this into Laplace's equation and then divide across by the potential x, y, z, what we obtain is okay, so now we have got terms which depend on x only, depend on y only, and depend on z only. And also what we have here now are ordinary differential equations. Okay, since these three terms are going to add to 0 at any point in the field, each one must be equal to a constant. Okay, so what we have here is d2x 2 is equal to c1 by x, d2y y2 is going to be equal to c2 by y, and for z It's going to be equal to C3Z. Okay, so these constants, of course, then add up to 0. So C1 plus C2 plus C3 is equal to 0. Now, an important next step, which we're going to do in the next lesson, is we had to determine which of these constants is positive and which is negative.